Okay, so last time when we left off, we had learned how to name alkyl halides. We also learned about naming branched alkanes. So we are going to pick up on our next slide here. So what we know about the IUPAC naming system so far is that IUPAC names are made up of 4 pieces. We have what are called locants. These are the numbers that indicate where the substituents are on the chain, or they indicate where functional groups are, like a halogen. So these are just those numbers that we put. It's the address of the substituent along the carbon chain. And then we have to list off our substituents. So that could be an alkyl group, that could be a halogen. We have our parent chain prefix. So the parent, remember, is the longest continuous carbon chain. And then we have our infix and suffix. And this is something we haven't really talked about because so far everything that we've looked at has been alkane based. So when you're looking at something like an alkane and you have, say the name like octane, we have our prefix that indicates that we have an 8 carbon chain. The infix is actually AN. The infix AN indicates that we only have carbon-carbon single bonds. The suffix E indicates that it is part of the hydrocarbon family. So there's no other functional group present really. Like yes, there can be a halogen, but there's nothing like an aldehyde or a ketone or carboxylic acid, something that would have its own unique suffix. So those are the 4 parts of a name so far. But we're going to introduce alcohols now, and alcohols are going to have their own suffix. So the first kind of change to our rules here is we're still going to start with the longest continuous chain, but the longest continuous chain has to include the hydroxyl group. The attendance code for today, does anybody remember what it was?
I think it was
9706.
9706. So now we're going to select the longest continuous chain that includes the hydroxyl. So it may not be the longest carbon chain in the structure, but it has to be the longest carbon chain that also has the OH group. We are going to drop the suffix E, which indicates that it's a hydrocarbon, and add all. So for example, a 2-carbon hydrocarbon is ethane, but a 2-carbon alcohol is ethanol. So we get rid of E and add OL. And then we number our carbon atoms, but we make sure that the hydroxyl group gets the lowest number it can possibly have. And then we indicate the position of the hydroxyl group using that number. I know I'm just listing off a bunch of stuff. We're going to do some examples. And then you list your other substituents in front of the name. So that's a lot of rules. We're going to actually just apply them now. So this first one on the top left, what is the longest carbon chain?
3.
3, okay. And are we going to start numbering from the left or the right?
The right.
Right. We want to give the alcohol the lowest number possible. Okay, so what is our family name? What is the 3-carbon family name?
Pent.
Not pent, it's the other P one.
Prop.
Prop. Right. So we're going to have propane as part of the name. We're going to give it the suffix all. And then we also have to indicate that the hydroxyl group is on carbon number 1. So that gives us the name 1-propanol. Now, the reason this is important is that look at the next structure. It is also a 3-carbon chain. It doesn't matter where we start numbering on this one, but the name of this compound is going to be 2-propanol. The common name for this is isopropanol. Okay, so let's look at the next structure. What is the longest carbon chain?
4.
4.
4. And do we start numbering from the left or the right?
Left.
Left, right. 1, 2, 3, 4. So what is the name of this compound?
2-butanol.
Yep. Or using common naming, this would be sec-butanol. Okay, let's do our next one. What is the longest continuous chain?
5.
5. And are we going to number from the left or the right?
The right.
Right, we want to give the alcohol the longest possible, or sorry, the shortest possible, lowest number. I went through several words there to get to the right one, but I made it. Okay, so if you're struggling a little bit with this naming, I'm going to break this down into kind of a list of steps for you. So your first thing is always, what is my longest carbon chain? And then you decide, where am I going to start numbering? Go ahead and write out those numbers. So that's what we've done so far. The next thing that you should do is decide, what is the family name here? So we know that we have an alcohol. That means our name has to end in "all." And we have a 5-carbon chain that we're trying to name. We're going to put this on our name last. So what is the family name for a 5-carbon alcohol?
Hexanol.
It's not hex.
Is it
Pent.
Pent, right. So this is going to end in pentanol. If you can't see the red on green, please let me know. I realize that's a horrible color combination. Especially if you're colorblind, you can privately chat me to switch up everything if you'd like. What else do I have to say about pentanol though? Do I have to indicate anything specific? Ignoring the methyl for now.
The location of the pentanol.
Right. So what do I have to put on here?
1 pentanol.
Right. So 1 pentanol. Okay, and then the last thing is I have to indicate where the substituent is. What is the name of my substituent?
Methyl.
methyl?
Methyl. And what carbon is it on?
4.
4. So this is 4-methyl 1-pentanol. Okay, does this make sense so far?
Yes.
So we want to keep doing this just step by step, right? So let's look at our next structure. We're gonna do this one. What is the longest carbon chain, including the hydroxyl group?
5.
5. Are we gonna number from the left or the right?
Left.
Yeah, because it's closer to the alcohol. Okay. We have 2 substituents that we have to worry about. If you want to start there, you're welcome to. What would I write out if I'm going to start with my substituents? We have 2 identical substituents, right? And they're both on carbon number 4.
4-dimethyl
Really close. You try 4 dimethyl. Okay, and then we need to name the rest of our molecule. What is the rest of this molecule called?
2-pentanol.
2-pentanol, right. So any name that you come up with should describe the molecule fully. So we've described that it's a 5-carbon alcohol. The alcohol is on carbon number 2, and then I have 2 of the same substituent, and they're both on carbon number 4, right? Our name is very, very specific. We know exactly what the structure looks like based on the name. Okay, next compound. We have an alcohol and a halogen on the same molecule. The alcohol is going to be our priority, which means we need to start numbering from the alcohol. So remember that a halogen is just another substituent. So we can start with 3-bromo, and then we just have to name our alcohol molecule from there. What is the prefix for 3 carbons?
Prop.
Prop. Okay. This next one is a little more complex. What is the name? Actually, first, before we do that, the alcohol is the most important thing on here. And the alcohol is coming off of the carbon chain. That's its longest carbon chain. So that's what we're going to focus on. And that means that the benzene ring and the methyl group are substituents off of our longer carbon chain. So that's how we have to approach this molecule. What is our carbon chain length?
5.
5. And where am I going to start numbering, from the left or the right?
Left.
Left.
Correct. Okay. What is the name of this substituent? It's been a while since I taught it.
Phenol.
Right. So as a substituent, this is phenyl, and we have methyl. And what is the name of our alcohol?
Pentanol.
Right. Specifically 1-pentanol, right? Between phenyl and methyl, which one comes first alphabetically?
Methyl.
Methyl, right. So that's how we're going to name this. We're going to say 3-methyl, 1-phenyl, 1-pentanol. So anytime you write out a name, like in case you had, just gone left to right with your substituents, you would have written out 1-phenyl, 3-methyl, 1-pentanol. Just always go back through and double check that you alphabetized your substituents, and that'll help you catch your mistakes. So if we'd gone through and said P, M, O, crap, and then you just cross it out and rearrange them. So just always make sure that you're double checking your name before you move on.
When you have a phenyl group, is this the only case where it wouldn't be like 1,1-phenylpentanol? Since both the alcohol.
Oh, okay. I see what you mean. So you only put your numbers together like that if they're identifying the same substituent. Since these are identifying 2 different things, you need to separate out the numbers. So this name very specifically says 1-phenyl. So we know that the phenyl group is on carbon number 1, and then we know that this one goes with the all. You'll also see at some point that there's a way of naming where you might write out 3-methyl, 1-phenyl, pentan 1 all. Later we'll understand why sometimes the number is put in the middle of the name. That's always a valid option if you want. But you always want your number to be as close to what it's describing as possible within the name. Okay, this structure on the bottom left now, what is the longest carbon chain?
2.
2. Okay. And it doesn't really matter where we start numbering because there are 2 alcohols on 2 different carbons in our 2 carbon compound, right? So previously we saw that if we had 2 of the same substituent, we used di. We're going to do the same thing here. The base of our name is still going to be ethane. We're going to throw the E back in and say ethane diol. So again, you want your descriptors as close to what they're describing as possible. So we say diol instead of saying diethanol, because that makes it unclear what the di is referencing. And then we're going to say 1, 2. Because you could also have 1, 1 ethane diol as a possibility. So you have to be specific that the alcohols are on carbons 1 and 2. Okay. Are there any questions about this page? Cool. Oh, look, I put all the names here. That's so nice. Okay. So next, how to name cycloalkanes. First, you're going to count the number of carbons to get the parent name. Add the prefix cyclo. If there's only 1 substituent on a cyclic alkane, it does not need a number. If you have 2 or more substituents, the rules get a little more complicated. We're just going to go through the rules first and then do a bunch of examples like we did with the alcohols. So if you have 2 substituents, you number starting with the first one that comes up alphabetically, and then you number in the direction that gives the next substituent the lowest possible number. So you decide clockwise or counterclockwise numbering based on which one will get you to your substituent first. If there's 3 or more substituents, you number in a way that gives the lowest set of numbers possible. So at this point, it doesn't matter which one comes alphabetically, you just want the lowest numbers, period. And if you have a single ring attached to a longer carbon chain, you have to decide which one's more important based on which one has the most carbons or which part has the functional group. So that's what happened in the previous example where the phenyl was a substituent. Phenyl was a substituent because the functional group was on the carbon chain. If you have more than 1 ring attached to a single chain, the rings become substituents. So this is a ton of rules. We're going to work through several examples on the next slide. Okay, so starting off very simply, how many carbons are in this structure?
6.
6. And what is our prefix for 6?
X.
X. So if this were a 6 carbon straight chain, we would call it hexane. But since it's cyclic, what do we call it?
Cyclohexane.
Yep, exactly. Okay. Now in our next structure, we have a cyclohexane as our base, and then we have a substituent. What is the name of this substituent?
Isopropyl.
Right. So what would we call this molecule?
Isopropyl cyclohexane.
Yep, exactly. The number 1 mistake on quizzes and exams is forgetting the cyclo part when you're naming a cyclic alkane. You can also use the IUPAC name if you wanted. What is the IUPAC name for isopropyl? Remember, we have our longest carbon chain of 2, so it's 1, 2, 1-methyl ethyl.
So would you accept either as a correct answer?
I would accept either. Okay, in our next structure, how many carbons are in our cyclic ring?
5.
5. So what is our parent name going to be? Yeah, pentane. And since it's cyclic, what do we call it?
Cyclopentane.
Cyclopentane. And what is the name of our substituent?
Bromo.
Right. So we have 2 pieces that we have to identify here, right? We have bromo and then we have the cyclopentane. And then once you have those 2 pieces, you just list them out. Right. So it's the same as describing anything in English. We're just using like kind of made up words here. So like say you see a dog on the street, you say, okay, I saw a dog. That's the bulk of what you saw, right? That's the big descriptor. But you're like, and it was brown and it had 2 white spots on it. So you might say a brown dog, I don't know, a 2 white spotted brown dog or something. That's essentially what we're doing here. We're being very, very descriptive. I know that you would never say a 2 white spotted brown dog, but we are trying to describe what we see in front of us. And then there just happens to be an acceptable order in which you list out those descriptions. Okay, so our next structure, we have cyclohexane, we have an alcohol, and we have a substituent. What's the name of this substituent?
Ethyl?
Ethane.
Ethyl, right. Okay. So the alcohol substituent is not just a substituent, it's also a functional group. So what does that do to the structure or to the name of the structure? How do we indicate it?
Ends in OL.
Right. And since it's a functional group, it's automatically the most important thing in this structure. So this is going to be carbon number 1. I'm going to erase these circles so that we can see more easily. Now, we have to, since we have 2 things on this ring, we have to indicate their relationship to each other by using numbers. So the question is, do I want to number clockwise or counterclockwise to get to the ethyl group?
Clockwise.
Right, we want to go clockwise because it gets us to the ethyl group faster. So we have to indicate that the ethyl group is on carbon number 3 of the cyclohexanol molecule. So we're going to say 3-ethyl cyclohexanol. And you do not have to indicate the number 1 for cyclohexanol because the alcohol is going to automatically be number 1. Now, in our next structure, we don't have a substituent that's automatically number 1. We have 2 alkyl substituents. So how do we decide which one is number 1?
Alphabetically.
Right, alphabetically. So what's this one on the right-hand side?
Ethyl?
Ethyl. And what's the one on the left-hand side?
Methyl.
Methyl. Okay, so this one's number 1 because of the alphabet. Are we going to number clockwise or counterclockwise?
Counter.
Correct. Okay. How many carbons are in the ring total?
7.
7. So what is the family name of this molecule?
Hept.
Right. So it would be cycloheptane, right? So let's go ahead and list off all of our substituents. We have 1 ethyl, 3 methyl, cycloheptane. Okay. Do we have any questions so far? Is this making sense?
It makes sense.
Okay, cool. Let's do the next one. This one has 3 substituents. So how do we know where to start numbering?
With the chlorine, because it takes precedence.
Actually, the halogens and alkyl groups have the same level of importance. Yeah, that's something we haven't really talked about. But yeah, halogens and alkyl groups are on the same level. So if we have 3 substituents, how do we decide where to start numbering?
Alphabetically.
No, it's not alphabetical. This is a random rule that was on the previous page.
It's the low.
It's which one gives us the lowest numbers, right?
Right, we want to have the overall lowest numbers. So where on the ring should I start numbering if I want to give the lowest numbers?
On the top,
Yeah, so if I start up here and say 1, 2, 3, 4, that's going to give me the numbers, whoops, 1, 2, 4. If I had started numbering at the ethyl group, let me change colors. That would give me 1, 2, 3, 4, 5, 6. Or that could give me like 1, 2, 3, 4, 5. So our best option that way would be 1, 2, 5. If I started numbering at chloro, I would have had, let me get a different color again. I would have had 1, 2, 3, 4. So my numbers would have been 1, 3, 4. So you can do this. You can, write all over your structure like this until you come up with the lowest possible scenario. Our lowest possible scenario is 1, 2, 4. So that's what we're going to use. I'm going to erase just everything. I made a bit of a mess there. No. Okay. Stop. I'm having drama with my computer. Okay. So 1, 2, 4. So now we just have to list these off in what order?
alphabetically.
Alphabetically. Okay. So we have chloro, which starts with C. We have ethyl, which starts with E. And methyl, which starts with M. So we're actually going to list them in the reverse numerical order, right? So this is going to be 4 chloro, 2 ethyl, 1 methyl, and what's the rest of my name?
Cyclohexanol. Cyclohexane.
Right, cyclohexane. And there's no space between them. I just ran out of room. So remember, you're
So
gonna.
you do number the first one if there's more than 2, right?
You number everything unless it's a functional group that becomes part of the suffix.
Gotcha.
So if it's a functional group that affects the suffix, it is automatically number 1 anyway, so you do not have to say number 1. However, if you had written 3 ethyl, 1 cyclohexanol, you wouldn't really be wrong. You would just be redundant, I guess. Okay, before we switch to our lower level here, which has kind of a different thing happening, are there any questions? Okay. Remember, I can't help you if you don't ask me to. So if you are stuck, please let me know. If you're just uncomfortable asking questions in front of the class, you can private chat me, or make sure you come to office hours. I'm not having office hours today, but I will have them tomorrow afternoon. I think I have to have them directly at class because I have to drive to campus to film something for the SI program. But I'll let you guys know during class. Okay, so along the bottom line, when we have a cyclic structure and a linear alkyl chain, we have to make a decision based on the number of carbons. So there are 4 carbons in the ring and 5 carbons in the chain. So which thing is more important?
The 5 carbons.
Right. So we're going to start numbering from the left. So this is a pentane chain, and we have a cyclobutyl substituent. So this is going to be 1, whoops. Sorry, writing along the bottom is difficult because the controls are down there. 1 cyclobutyl pentane. Okay, and then in our next structure, we have a different scenario where we have 2 cyclohexane rings. And when you have 2 rings coming off the same chain, you end up giving the chain preference just for ease of naming. So at this point, we have a propane chain with 2 cyclohexane substituents. So 1,3 dicyclohexyl propane.
Do we have to number it like 1, 3, or can we just do dicyclo?
No, because you could have them both on carbon number 1, or you could have 1, 2, or you could have 2, 2. So the position is actually important. Although having them both on the same carbon would be a nightmare space-wise, but you do have to indicate where they are. Okay, any questions on this page? Okay. All the names. Okay. Yeah. Okay, how to name bicyclic alkanes. I'm gonna skip over this. You will see it once, I think, real fast in a reading question, and it'll be an extra credit question on the exam. But what I've found in the past is that the naming of bicyclic alkanes is really challenging for most people, and it's a little extra complicated. You can work on it on your own and get some extra credit points if you want, but it's not worth putting the entire class through during lecture. So we're gonna skip over it. It is really fun, I think, but just because I think it's fun does not mean it's valuable to your education. Okay, so how to name alkenes and cycloalkenes. So notice what we've subbed out is the AN, which was our suffix, or sorry, our infix for an alkane. And we've subbed in EN, which is our infix for an alkene. So we have a double bond now. So just like with the alcohol, we're going to choose the longest chain that contains the alkene, and this is now our parent chain. We replace the ANE suffix with ENE. The numbering of the chain must go across the double bond. I'll demonstrate that in an example. And you want to give the alkene the lowest number possible. And then you need to include the locations of all of your substituents. So notice these rules are not different, right? The only thing that you have to be cognizant of is that you number across your alkene. So what we mean by numbering across the alkene is that a number must go across the alkene. Your numbering scheme has to go through it. So if you have a cyclic alkene, that's where it becomes the most important. So we're going to start numbering along the chain that includes the alkene. This first one's much easier because it's just a 4-carbon alkene. So how many carbons? This is 4, right? What is our prefix?
Butte.
Butte, right? So what would be our parent name?
Butene.
Butene, right. And we have to indicate the position of the double bond. What carbon does the double bond start on?
1.
1. So this is 1 butene. Okay. Let's do the next one. How many carbons do we have total?
5.
5. And do we number from the left or the right?
The right.
From the right, because we'll get to the alkene faster. Okay, so does anybody want to just shout out the name of this compound?
Pentene.
2 pentene.
Yes, 2-pentene. So yeah, pentene is correct, but you got to be specific. Okay. Next, what is our longest carbon chain?
4.
And am I going to start numbering from the left or the right?
The right.
Are we sure? If we number from the right or the left, the alkene doesn't change, but what does change?
The methyl group.
Right. So we want to number from the left so that everything gets the lowest numbers possible. Okay, so let's ignore the methyl group for a second. What would be the name of this alkene?
Butene.
Not just butene,
2-butene.
2-butene.
2-butene. And with the methyl group, what's the name of this compound?
1-methyl 2-butene.
Two.
Or I mean, 2-methyl 2-butene.
Right.
There we go.
Okay. Next one. Do we number from the left or the right?
Left.
The left. Right. So sometimes like you don't have to come up with the number of carbons first. As long as you know what side you need to start numbering from, you can get it from there. So this is a 6-carbon chain. So let's ignore our substituents for a second. What is the name of our alkene?
Two hexene.
Right. Okay. And then our substituents, we have 2 of them and they're the same. So what do we need to write to describe them?
Dimethyl.
Dimethyl. And what's the numbers that go with them?
2,5-dimethyl.
Right. Cool. And you can also insert the number into the name if you wanted. So you could do bute 2-ene or hex 2-ene. That's not so necessary right now, but later when we end up having multiple functional groups on a molecule, then it becomes kind of necessary. So we'll look at examples that do that later. Along the bottom here, I just wanted to give you some common names here. So ethene is the IUPAC name. In parentheses, you see ethylene, which is the common name. The common name is the one that's usually used by industry. So like in the polymer industry, they would call this ethylene, and polymers that come from ethylene are polyethylene. So your PET polymers. Propene is called propylene industrially. And then 2-methylpropene is isobutylene in industry. But usually I'm looking for the IUPAC name, and I will specify that. So in our cycloalkenes, you want to give the carbon atoms of the alkene the 1 and 2 positions. And then give your substituents the lowest numbers possible at the first point of difference. I'll explain that in a second. In cycloalkenes, do not give the number of the double bond, since it is always number 1, unless you have more than one alkene. If you have more than one alkene, you do have to give the numbers. Alcohols will have the priority. So if you have an alkene and an alcohol on a cyclic structure, which one is going to be number 1, the alkene or the alcohol?
Alcohol.
The alcohol, right. Cool, okay, let's practice. So in this first structure on the left, where are we going to start numbering?
The top, top of the circle.
Yeah, and are we going to go clockwise or counterclockwise?
Clockwise.
Yep. Okay, so if we were ignoring the methyl group, and we can even, no, we're not going to ignore the alkene, that would be too much. Ignore the methyl group for now. What is the family name of this molecule?
Cyclopentene.
Right, cyclopentene. And then we have our methyl group. So this is 1-methyl cyclopentene. And notice we are not indicating where the alkene is because it's automatically on carbon number 1. Okay, so in our next structure, it's a little more challenging, kind of, I guess. Basically, you have to decide between, let's call this carbon A and carbon B. Which one is carbon number 1?
A.
Yes. So if we start with A and number clockwise, because remember your numbering scheme has to go through the alkene, that's going to give us our lowest possible numbers. Oops, that's a 5, sorry. Okay, so what is the parent name?
Cyclohexene.
Right, cyclohexene. And our substituents, we have 2 identical substituents again.
It's 3,5-dimethyl cyclohexene.
Yeah, exactly. Cool. Okay, next structure. What is carbon number 1?
The alcohol.
Right. Okay, and then are we going to number clockwise or counterclockwise?
Clockwise.
Yep. Okay, so we have our alcohol on carbon number 1. We don't have to say that though. And we have a methyl group on carbon number 2, and our alkene starts on carbon number 2. So let's think about this piecewise. So if this had nothing else on it, like if the alkene wasn't here and the methyl group wasn't here, this would be cyclohexanol, right? But we do have an alkene, so we know that our parent name is going to have the EN infix. This is where using those numbers within the name can be helpful. Whoops. cyclohex 2-ene-all can help. So putting the 2 next to the ene can help clarify that. And we also have to say 2-methyl. Oops, no hyphen there. I just tried to mentally fill the space, I guess. Okay. So yeah, this is a situation where inserting the number can help clarify that.
Would we be able to write it 2-methyl and then 2-cyclohexanol?
You could, yeah. Okay, next one. What is our most important carbon? All right, let's make it simpler. Are we gonna number from the left or the right?
The right.
Yeah, from the right. We want to give the alcohol the lowest number. Okay. So what is our parent name?
Pentanol or pentene.
Yeah, pentenol is our situation. Since this is not cyclic, we do have to indicate that the alcohol is on carbon number 2. So this is where you definitely are going to need to do this because it's about to get a little crazy. So this is going to have 4-methyl as our first bit of our name. And then we know that we want to say pentenol. It's going to be 3-ene-2-all. This is a situation where you have to put the numbers in there. Otherwise, it's just not going to be clear. If you wrote 3,2-pentenol, that's not as clear as saying pent 3-ene-2-all. So anytime you write out a name, like say you had written out 4-methyl pentenol and you forgot about the numbers, ask yourself, does this name describe this molecule? I have my alcohol. Does it say where the alcohol is? No, it does not. So I need to insert the 2. I have an alkene. Do I know for sure that it's on carbon number 3? No. So I need to insert my number, right? So go back through and check yourself and make sure that you're describing the molecule fully.
So you'd only use this sort of like form of like conjunction for now, at least when you have some sort of alkene with an alcohol group attached to it.
For now, yes. Yeah. If your molecule was a little more on the complex side, you would need this.
Okay.
So more than one functional group, essentially. Okay. There are also some common alkene substituents. So this could be ethanol or vinyl. Ethanol is the oops, that's not how you spell that. Ethanol would be the IUPAC name. Vinyl is common, but it's widely used. This would be 2-propenol, but allyl is commonly used. Because remember, those IUPAC names, we want them to be as simple as possible. And allyl is a nice way of describing this quickly. So vinyl and allyl will be used fairly often. So for example, this first molecule can be called bromoethene, or it could be vinyl bromide. The next one, we could call it 3-chloropropene or allyl chloride. Ethenyl cyclopropane or vinyl cyclopropane. And then this one shows very nicely why allyl is a great substituent name. There shouldn't be a space there either. I apologize. So 3-prop-2-ene-1-il cyclohexane 1-all, or you could just say 3-allyl cyclohexanol. So this is a circumstance where using the common substituent name is perfectly fine.
Where's the 3 group on that last one?
Where is
Like,
where
yeah,
is it?
the 3rd carbon on that one.
Oh, so the 3 is referencing the position on the ring.
Yeah, I see it.
Yeah. Okay. So how to name alkynes, not very different from our alkene rules that we just went through. So instead of saying so instead of this being a pentane, it's now a pentyne. Whoops, I numbered from the wrong side. That's embarrassing. Okay. So 2-pentyne. In our next molecule, we see that we have both an alkene and an alkyne on here. The alkene ends up getting the precedence. So alkene is going to have the higher priority. It's going to be number 1. So we number this molecule 1, 2, 3, 4, 5. And when we get to the alkene chapter, we're actually going to learn that we're not technically done with alkene naming. We're still missing a key piece, but we're going to come back to it later. Okay, so this next molecule, where are we going to start numbering? From the right or the left?
The right?
Mm-hmm. Remember, if you have a hard time seeing the carbons of the alkyne, you can use dots to help you separate them out. So what would be the name of this molecule on the right-hand side?
1-chloro-2-butyne.
Yeah, exactly. Okay, next molecule, what do you think is more important, the alcohol or the alkyne?
Alcohol.
Alcohol.
Right, because remember the alcohol was more important than the alkene, and we just learned that alkene is more important than alkyne. So far, the only priority list we have is alcohol is greater than alkene is greater than alkyne. So what is carbon number 1? In this molecule?
The one by the hydroxide.
Right. So what is the name of this molecule?
Three butane, 1-all.
Yep. Okay, and then our other example is essentially the same molecule, but we added on some ethyl groups. So, we need to number with the methyl group. So we have a pentyne now, and our alcohol is on carbon number 2. So we have our methyl group. So 2-methyl, 4-pentyne, 2-all. Any questions on alkyne naming?
Would that last one not be 2-dimethyl?
No, it's not dimethyl because this one of the methyl groups is carbon number 1. Because
Oh.
our longest chain. Yeah, I went through the same process. I think it's because I put these 2 examples together, which was really mean. Also, if I had written it out as like this way instead, it would be a lot more obvious. And it would still be the same molecule. Okay, so physical properties of alkanes, we've already kind of covered this earlier, Basically, what I want you to remember is that the larger number of carbons in an alkane or a cycloalkane, the higher the boiling point and the higher the melting point. That's all. And this is going to be just because you're going to have greater London dispersion forces if you have more carbon atoms present. So that's all I want you to take away from that. And we looked at this information previously as well, just not as much of a chart. An unbranched alkane is going to have a higher boiling point than a branched one because the surface area is greater. So greater surface area versus if it's cyclic. Or if it's branched, it becomes more spherical. Do we remember this from, I think it was chapter 1 that we talked about this in. Okay, so that's the end of our naming portion. Now we're moving on to conformations of alkanes, which is really fun, but also more challenging. This is gonna be one of your first like really big conceptual situations here. So what we need to remember is that two groups that are bonded by a single bond can undergo rotation around that bond with respect to each other. So actually have models. I'm going to stop sharing for a second so that you can actually see me. Okay. Can everyone see this structure?
Yep.
Okay, I'm actually going to move and create a background here. So if we have an alkane, I'm going to take off the green block. Oh, I just lost that in between my couch cushions. Okay, so if we have an alkane such as butane here, right now I have it drawn out just like how you would draw the line bond structure of butane, right? But a sigma bond can have rotation. So we could also draw it in this shape where we have these three in our normal shape and then draw this methyl group down. This would be the same molecule. I'm not changing the molecule at all. I'm not breaking any bonds. They have free rotation. Like I can take this and kind of like twirl it like a party favor. And in reality, that's what these molecules are doing. They are not just sitting there perfectly in space like this. They have rotation. And so they are, in fact, constantly moving. And it's these different conformations, which is what these different shapes are called, that we're discussing in this chapter. So when we say conformation, we mean that it's in a different shape just due to rotation. The other thing that we have to remember is that a double bond anytime that you have a pi bond, you actually are not going to have rotation. So those molecules end up locked in place. So here's my pi bond model. It's planar. This is not going to have rotation because we have multiple bonds holding it together, right? So it's not going to be able to turn. So when we're talking about conformations, we are talking about single bonds only. So I'm going to go back to sharing a slideshow. Okay, so conformations are temporary molecular shapes that result from a rotation about a single bond. A conformer is each possible structure of conformation. So our perfect line bond conformer versus our kind of C-shaped conformer here. Conformational analysis is the analysis of energy changes that occur as a molecule undergoes rotations about single bonds. We're going to get into a lot of detail about conformational analysis. So for example, hexane, in the pictures drawn there, you're seeing hexane drawn in several different ways. I feel like one of these, I have got to edit this slideshow. This one has too many carbons. So eliminate one of those carbons. This is not the first time I've used this slideshow and had that problem. This is actually maybe the 4th time. I just never remembered to fix it. So this is hexane. Here it is looking pretty and perfect, like a line bond structure. But you can rotate around these bonds and create quite the jumble. The thing is that when these bonds rotate, you're forcing them to have different interactions than they did when they were sitting in a different conformer. So that's what conformational analysis is going to discuss. So this brings us to Newman projections. A Newman projection is a way of looking at a molecule where you can easily observe the potential interactions between atoms attached to the same carbons. So when we are looking at our hexane molecule, I'm gonna stop sharing again for a second. If you're having a hard time seeing me, you can pin my picture if you need it to be bigger. So we can look at hexane this way, but let's say that I wanted to look at hexane and observe the effect of rotation on carbons 3 and 4. You can turn hexane so that you're looking specifically down carbons 3 and 4. And what you would see if you're doing this is that there are these hydrogens here, and currently I have them staggered, and I also have the rest of the carbons opposite each other. So carbons 1 and 2 are down here, carbons 3 and 4, or sorry, 4, 5 and 6 are up here, and we're looking at 3 and 4 down the middle. That is what a Newman projection does. It looks down a bond and looks at everything that's coming off of that bond. So in this molecule here, we are looking down this bond, and we look at the front carbon and the back carbon, and then they get combined into this kind of Mercedes symbol shape here. So we can look at this carbon and say it has a chlorine, an ethyl group, and a hydrogen, and the back carbon has a methyl, a hydrogen, and an alcohol. Methyl, hydrogen, alcohol. We're gonna look at a lot of these. So for ethane, you have only 2 carbons and you have 6 hydrogens. So the hydrogens on the front carbon are in orange. The hydrogens on the back carbon are in blue. The Newman projection is showing us this view here. So the 2 carbon atoms are eclipsing each other. They are on top of each other. And the hydrogens are all staggered. This is actually called the staggered conformation. The torsional angle between HA and HB is 60 degrees. And the torsional angle between HA and HC is 180 degrees. We can also have the eclipsed conformation. So the way that this is done is our staggered conformation had it like this. To get to eclipsed, we're doing a 60-degree rotation. So it's just a very slight rotation about the sigma bond of ethane. In the eclipsed conformation, the torsional angle is 0 degrees. So there is an energy cost to these rotations. When the hydrogen atoms are in the staggered position, they are as far apart as they possibly can be. And if you remember when you learned valence shell electron pair repulsion theory or VSEPR theory, the goal of that orbital hybridization to create those different VSEPR shapes was to get the electron pairs as far apart as they possibly could be. So in our staggered conformation, the electrons that are in those bonds, in the covalent bonds to the hydrogens, are as spread out as they possibly can be. So remember, there's electron density in this bond, in this bond, and this bond, and in the ones behind it. So when they're staggered, they are far apart. They are not taking up the same space. plus the hydrogen atom takes up space as well. When you eclipse them, you are forcing them to take up some of the same space. So they are actually closer together when they are eclipsed than when they are staggered. And that's why it's a higher energy conformation. And then, of course, it gains that energy back when you take it back to staggered. So while these are freely rotating, which position do you think molecules spend more time in staggered conformations or eclipsed?
Staggered.
Staggered, right. The staggered is the preferred conformation. So if you have a chemical reaction that depends on it being in the eclipsed conformation, is much less likely to occur than a reaction that is dependent on the staggered conformation. That's a much further in the future concern for you. By further in the future, I mean next week. But so remember, higher energy is less stable. Lower energy is more stable, and electron domains like to have their space. Okay, so we're going to do the conformational analysis of butane. So if we look at butane down the 2,3 carbon-carbon bond. So this is carbon number 1, 2, 3, 4. We're putting our eyeballs right here. This is going to be carbon 1. Carbons 2 and 3 are eclipsing each other in the middle. They exist right here. And then this is carbon 4. Does that make sense to everybody? If this doesn't make a lot of sense to you and you feel like you need to hear all this again, I am going to post this presentation later. And I also made a separate video about Newman projections a couple years ago, and I posted that on our website already. Okay, so this is the Newman projection for butane, and this is going to be the staggered projection. But there are also different types of staggered conformations. So when you have your methyl groups directly opposite each other across the Newman projection, this is the lowest energy conformer because the methyl groups, which are the largest substituents coming off of carbons 2 and 3, are far apart from each other. And then you have a 60-degree rotation in the clockwise direction, which staggers a methyl and a hydrogen in 2 different places. That's going to be a higher energy conformer. You rotate again, and you are back to a staggered conformer, but notice that the methyl groups are now next to each other. This conformer is called gauche. It is still lower energy than any eclipsed conformer, but it's not as low energy as our anti-conformer. You rotate again 60 degrees clockwise, and you get your highest energy eclipsed conformer. So notice now the methyl groups are eclipsing each other. Rotate again, you're back in a different gauche conformer. Rotate again, and you're back into a different eclipsed conformer. Does this make sense? I've never actually taught this part online before. Usually I'm holding up models and showing them to you in live space. So please ask questions if this doesn't make sense. There's some animation. Okay. So with all of these conformers on an energy chart, you can see our anti-conformer, we go up in energy to eclipsed, we go back down to gauche, but notice it's not as low as anti. You go back up to your worst eclipsed conformer, and then we repeat the same thing. Okay, so we're going to talk about cycloalkanes now and the different forces affecting them. So cycloalkanes do not have the same relative stability as linear alkanes due to their ring strain. So ring strain is comprised of 2 different things. One is angle strain. This is the deviation from your ideal bond angle. So remember that when you have a cyclic alkane, those carbons are still sp3 hybridized. what is the ideal bond angle for an sp3 hybridized carbon?
$90.
Not 90.
Is it 109?
Yes, 109.5. But when you put them into a ring, you are going to be deviating from that angle. So for example, if I take a molecule of butane and I force it to become cyclic, my model doesn't like that. You can actually see that it's buckling in a couple places along the model. And this is how I frequently break my models, by the way, is demonstrating angle strain. But what angles are we forcing these carbons to have? What is this angle I'm trying to force?
90.
90, right? When it wants to be 109.5. So that creates some strain. The other issue is if we look at the Newman projection along a cyclobutane, this is all currently eclipsed, right? And it cannot escape that. What we're going to learn in a second is that it's actually going to create a bend in the structure of cyclobutane to try to alleviate some of that. But right now we're mainly talking about these angle strains. Torsional strain is this part here. So torsional strain is the result of the dispersion forces that are caused due to the restricted conformational mobility. That's what I was showing you about how the hydrogens were being forced to be eclipsed across that bond. So cyclopropane is even worse. I actually can't make a model at all with this model set of cyclopropane. I did do it in class once and it broke and snapped directly in front of my eyes. So I had a little bit of a scare because it popped. So these are still sp3 hybridized carbons. They want to be 109.5, but this angle actually ends up being closer to 60, which is very, very rough on that carbon. This is directly defying the laws of Vesper theory. Right, so then all of the carbon atoms in cyclopropane are coplanar, meaning they are in the same plane. And all of the hydrogen atoms, if you were to look at the Newman projection down any one of these bonds, all of those hydrogen atoms are eclipsed. So there is nothing good about cyclopropane. It's experiencing intense ring strain and torsional strain. Cyclobutane does something a little different. It's actually going to push two of the carbon atoms out of plane so that you create kind of a butterfly structure. And it does that in order to relieve some of the ring strain and some of the torsional strain. So the internal bond angle ends up being about 88 degrees. And it's not going to be planar. So it does this in order to relieve a whole bunch of the torsional strain. Cyclopentane also does something similar. If you make a model of cyclopentane, and have it all in the same plane, it's actually really difficult to keep it all in the same plane. Because when you do that, you're gonna have fully eclipsed bonds again. But if you pop one of the hydrogens out of plane, just one, so all the other four are still in the plane, you create staggered conformations along some of the bonds, and that's going to be preferable. So this is called the envelope conformation. So these bond angles are actually pretty close to what they should be. Does this make sense so far? Okay. So our last bit here is cyclohexane. This is definitely the biggest part of our conformation section. And we're definitely not going to finish this today. We will talk about this a lot tomorrow, and then we'll get into chapter 5. But cyclohexane has two main conformational forms. You can have the chair form or the boat form. And I actually have a model pre-made of this. I'll use my smaller one so you can see it better. We are used to seeing cyclohexane drawn like a hexagon, right? Just want to stop sharing for a second. So we draw cyclohexane like a hexagon, but that takes away from the 3D structure. When you look at it in 3D, you actually have this interesting thing where you have one carbon up, one carbon down, one carbon up, one carbon down. So you kind of have two separate planes of carbon atoms. You have a lower plane and an upper plane. And this gives you the chair shape. I'll use my big one so you can see the chair. So that chair shape that was drawn on the slide, you can actually kind of see it if you tilt the model. So here's our chair shape. The other thing that you'll notice is that I have my hydrogen atoms in different colors. There are 6 hydrogen atoms that are blue, and they are kind of around the periphery of the structure. And then there are 6 hydrogen atoms that I have in white, and they are going up and down through the structure. And they actually have different positional names that we'll get to in a second. And in my other model, it's the same thing. I have green and white. So green around the side, white going up and down. And then that other conformation is the boat. In boat conformation, you bend 2 of the carbons down and have 4 in the same plane. So the chair form is the most stable. The boat is the less stable conformer, but not the least stable. This is a kind of complex Newman projection of the chair form. This would be looking down 2 bonds. So that'd be like taking it and looking at it like this. I don't know if you can see that on a camera, but it's looking at it this way. What you can see is that all of the hydrogens on the chair form are actually perfectly staggered. So no matter what Newman projection you look at, every single one is staggered. So do you think the cyclohexane really suffers from any sort of angle strain? No. And it doesn't really suffer from torsional strain either. Every single one of these carbons is perfectly happy. I've never broken one just from having it sit in a cyclohexane ring. I have broken it before by being too enthusiastic about my chair to boat conformations. But anyway, and then in the boat form, you actually have a problem where all 4 of the carbon atoms that are in the same plane, they are all having highly staggered interactions. So, or sorry, eclipsed interactions. So the boat form is a problem because you have a ton of torsional strain. You don't have any angle strain, but an excessive amount of torsional strain. And then there's also this other issue called flagpole interactions. So in your boat conformation, notice that these 2 hydrogens up here are almost in the same space. And remember, they take up a lot more space than these little spheres and sticks indicate. And then also imagine if these were not hydrogens. Imagine if we had an alcohol or a methyl group or something. These would really be taking up the same space. So these are called flagpole interactions. And then there's also this other form called the twist boat, which is lower energy than the boat conformation, but it's still not very good. And I actually cannot make my model do twist boat. I can't figure it out. I've tried so many times. So here is your conformational analysis chart showing energy versus conformation. So notice the chair is the lowest energy conformation by far. It is a very happy conformation. Boat is up here about halfway, and then you also have this disaster called half chair, which is halfway between chair and boat. So when you're in the half chair, that actually forces 5 atoms to be in the same plane. They're all going to be eclipsed as well. So these are our conformations. Our next topic is the substituted cyclohexanes. It's 11:38, so I don't think that we should start this. But what I do want to tell you is that this particular topic, and I know that I've lost a lot of your attentions. I know that when your cameras are off, a lot of you probably aren't paying attention, but this is really important. This next bit of the chapter tends to hurt brains. Like, it is a little difficult to swallow. It's not going to be easy to get it from me in 30 minutes of a lecture. So you need to read ahead on this. You need to look at my slides. I would start with the slides. If the slides don't make sense, crack open the textbook. I've assigned that reading anyway. You have to answer some of those questions. Please do this before tomorrow. Remember that you are taking a quiz tomorrow. I'm not going to quiz you over this part because we haven't learned it. Your quiz will largely be alkane and alcohol and alkene naming. So go over your naming. That's the big chunk of it. But for your exam, you will see these conformations. You'll see Newman projections, and you'll see substituted cyclohexane conformations as well. And this is not the last thing that we're learning before your exam. So do not put this off until after class tomorrow. After class tomorrow, we'll start at chapter 5. Chapter 5 is harder. So we have really big chapters this week. You need to put effort into that. I see a question, when do I post the old tests? I'll post them tonight. I'm not going to post them today. I do want you to study chapter 4 today. I want you to put some effort into that before class tomorrow. Otherwise, I think it's going to be really, really challenging.
I have a quick question. Iris spectroscopy. I know we kind of like flew through that, but we did have to memorize like all the oh God, I'm blanking. The strength and stuff. How relevant is that going to be for the quiz?
I'm not going to put that on the quiz. You'll see it on the exam, but not the quiz.
Okay, cool.
And then on the practice exams, I think there's 1 or 2 questions about it. So you'll see what it looks like on an exam in the practices.
Okay, awesome. Thank you.
All right, no problem.
The IR, like reading homework and stuff, is harder than what will be tested on.
Yes, the homework is much more challenging.
Yeah, that's what scared me more than anything. I was like, I don't remember any of this.
Yeah, you know, the questions in the homework that are like, what functional group is most likely represented by this spectrum? Those are the ones that you're going to see on the test, or where it gives you an IR and it gives you several molecules to look at, and you're supposed to pick based on functional group. You're going to see that as well. So that's what I would focus on, and getting the molecular weight from the mass spec. But I'm not going to test you over fragments or anything like that. I see some stuff in the chat. Okay, I think I got everything in the chat. Okay, any questions? Cool, I'll see you guys tomorrow. What?
I'm sorry. The office hours tomorrow.
Office hours tomorrow will be directly after class, so I'll have to start them like at 11:40.
Okay, thank you.
All right, see you guys tomorrow. Read chapter 4.
Thanks, Dr. B.
Thank you.